Okay, as with the beginning of every class, I should like to review a little bit the objective of this class, right? We're talking about big data and data analytics. And as I said in the very first class, big data entails a lot of things. It's a whole technology stack. There's a big chunk of it that requires a technological development in terms of computing platform. This is things like MapReduce, how it's implemented as Spark, Hadoop, and so forth. And we can't cover that really in class, realistically. First of all, I'm not the Hadoop or Spark guy, so we would need a proper lab to do that sort of thing. It's more like a programming. And in real life, it's only reorganization where you need that kind of complete technology platform. But what we would learn is the extension of the data into the big data. In particular, we're not going to focus so much on the volume or the velocity. We're going to focus on variety, right? So after giving you guys a little bit of introduction and overview of how big data relates to analytics, okay? Then we go quite a bit into machine learning. Machine learning, which again, roughly speaking, or by most convention, is organized into supervised learning paradigm, unsupervised, and reinforcement learning, right? And just as for big data, we don't focus so much on the volume or the velocity in this class. Here, we also don't focus on the reinforcement because it's not used so much in the analysis of data or data analytics. So we'll focus mostly on this two, right? Right? And we went through sort of like the middle part of the lecture, the middle part of the class, having to do with unsupervised learning and supervised learning, right? If you will recall, we did that. For unsupervised learning, we focused on clustering, which I think will be used in the project. Also, dimensionality reduction, which I understand is also used in the project. But most of the project I see is focused on supervised learning. Okay, and supervised learning, again, roughly the category I tend to go with would be something like a neural-based, neural learning, or sort of like tree-based. There are also some statistical learning and so forth, but mainly two classes: the tree-based, decision tree type thing, random forest, gradient boosted trees, and the neural learning, which again has number of variety. For example, we start with MLP, multi-layer perceptron. That's really the beginning of everything, so to speak. And then I come back to focus on this thing, on the variety bit, right? Then I have to echo. Yeah. So the variety. Hello. Echo back. Yeah. For variety, obviously we can deal with sound, we can deal with all kind of stuff, but for this class, we went into picture, or right? Basically pixelated, digitized picture, which could be black and white, or it could be red, blue, green screen. Okay? Now, putting this together, using
when you're dealing with data that comes in the form of picture, and you want to do some kind of analysis, mostly object recognition or analysis of the content of the picture, you put this together with this, and we analyzed or we studied the tool 2 weeks ago of CNN, convolutional neural network. Okay, so convolutional neural network essentially has multi-layer perceptron at the end to do the analysis, to do the object recognition. But the pre-processing part, instead of doing classical convolution filter like we were doing in the 80s or in the 90s when I was a student, you would use convolutional layers that learns the convolution. Okay, so that was the breakthrough. I guess I mentioned 2011, 2012 as the breakthrough year. Okay. Then last week we talked about variety of graph. Okay, this is an emergent phenomenon as well with respect to big data. Is that it's not sort of like a database that you say, oh, this person has certain characteristic, but this is also like this person is connected to that person, or this city is not connected to that city, or this bank is connected to that bank. So graph again, mathematical graph is not plots, right? From now on, we'll call that plot or chart. Graph in this case would be interconnected node. Okay, it could be symmetric, two-way, right? It could be directed and so forth. So that's graph. Now, we spend a bit of time talking about centrality analysis, okay, which maybe I didn't spell out, but if you want to tie it with machine learning, you can think of it as more like an unsupervised technique. Okay, for example, when we use eigenvector decomposition of adjacency matrix, I get centrality analysis. So that's over here. Okay. Now, today is the last class. We're going to cover something new. Okay. Next week is a project presentation. So this is the last opportunity to learn something new. So we'll go to this last bit of the variety. Okay. Again, there are other things like spectral, whatever, but we're going to deal with the last thing, which is words or text. Okay. And to tie that with supervised learning, okay, we wanted to tie the supervised learning. Okay, but what we are going to learn today is called word to vec. Okay, it's not supervised learning. Not. It leads to supervised learning, but it doesn't quite. Okay, maybe I should make an analogy. If you have picture, right? You go to CNN and you do something like some kind of result, right? There's a cat or dog or whatever. Now, remember I told you that inside CNN, you can think of it as two parts. One part is MLP and one part is convolutional stuff. Okay, maybe max pooling and all other things in there. But you can think of it as this bit turns picture or digitized picture into vector, into numbers, okay? And then feed, and then you do this. Well, words kind of go through the same kind of loop, but here it's called word to vec. And it turns words into numbers, okay? And today, it stops here. Let me say that again. Today, it stops here because once you turn words into vectors, then the rest of the analysis, you know, you apply any kind of machine learning technique. Now, obviously, you're going to be applying like MLP, something like that, right? but it's not kind of like connected in one architecture. So it's slightly different approach. Okay, with picture, you kind of like focus on the convolutional part so much that you put multi-layer perceptron, stick it to the end, so to speak, and call the whole thing CNN. It's like a whole package deal, right? So picture analysis turns into vectors in here somewhere, right? And then to do the object recognition, whatever, feed forward. But with words, the analysis kind of stops here. The essence of today is to turn words into numbers. Once you turn words into numbers, then the application is open. So it's not a package deal, sort of like CNN. Okay. So this is something that if you read on your own or you study on your own, you won't understand. It's a little bit confusing. So it's word-to-vec, supervised learning, unsupervised learning, well, it's not reinforcement learning for sure. Okay. But is it supervised learning? It's not, because at the end of the day, you don't have a ground truth of what you want to do. You just turn words into vectors. Okay, you just turn words into vectors, but you turn it into vector in such a way that words that are close together in context are numerically close together. So in a way, it's a bit like unsupervised learning. It's a bit like that. So I would call this, I would consider, if I were to force to say, it is called unsupervised learning. Okay, but the technical word, the real technical word, is called embedding. So that's a new word you learned today, embedding. So you embed objects, in this case words, into vectors. Okay, so embedding, you can say, is short for vector embedding. So you embed something into vector. Okay, so embedding is a new word today. It's a new process you learned today. It's turning objects into vectors of number. Okay, if I don't want to deal with you, I don't like people, but I have to deal with all of you, I can embed a person into a vector. So I turn you into a vector and analyze you as a vector. So you can call that human embedding. Okay, we don't really do that, but that's a concept. The reason I mentioned that is because then today it's called word embedding. The algorithm is called word-to-vec. See, word-to-vec, turn words into vector. But technically it's called word embedding. But once that framework is established, then people come over here and do all sort of embedding. They do graph embedding. They can do, say, spectral signature embedding. They can do all kinds of embedding. Okay, and this is the future direction of research. This is what is going to be happening in the next 5 years. This is that more, I would say this is probably in AI and machine learning, this is the top 5 areas, let's say, in the next 5 years. Okay, it's embedding a whole bunch of stuff. Okay, it starts with word embedding, with word-to-vec. Okay, this technology is about 2-3 years old already. Okay, but now people are trying to embed other things. What does it mean? What it means is that I don't treat individual objects as items. I treat individual objects as vector inside a vector space, such that there's a closeness in context of some sort. Okay, so you can imagine that if I turn you into vectors, okay, because you guys are working in the same group, let's say you're working in the same team, the vector that represents you and vector that represent you will probably be close to each other, right? That's the concept. That's where we're going. Okay, so once you have one, you can have two. Once you have two, you can have three. One is embedding word. Now they're embedding graph, then they're embedding picture, they're embedding this, they're embedding that, and so forth. They can do anything. You can think of any kind of analysis as objects, right? And then you embed it in such a way that objects that are close together in some kind of phenomenon, Okay, you can imagine, say, something like embedding pictures. Okay, pictures in this case, I mean movies, embedding movies. You can embed a football player. You can think of it that way. All right. So this is a very powerful concept, this kind of embedding. And that's what we want to get at today. Okay, but again, it's not sold as a package, so it's not a whole learning thing. Okay, it's just I just turn word into vector. The word to vector, if I were to be forced to making a distinction, what kind of machine learning paradigm it is unsupervised. Okay, it's not doing anything. It's not saying that this word means anything or this person is anything. It's just saying, well, I have a bunch of words. I want to turn them into vectors such that they are close together if they are similar in context. Something like that. Okay? So in a vector space, cats and dogs will be closer together than cats and refrigerator. Something like that. Okay? Now, why do I make a big fuss out of the fact that word2vec is an unsupervised learning? Well, because inside word2vec algorithm, the steps that you take inside to create this word2vec transformation will rely on supervised learning. So people can get confused quite a bit. Okay? So when you dig inside here, this algorithm go inside here, it employs supervised learning technique to do that. Okay? Does that make sense to you? Okay? So machine learning, again, if you have some kind of ground truth, you have X goes to Y, and if this X predicts this Y and you get the right prediction, yes, good. If it's not, then you tell the neural network, no, it's not good, go back, right? That's supervised learning, okay? But if you give it some kind of closeness, some kind of criteria of how to organize data, and you give a whole bunch of data to the machine, and the machine just reorganize the data or packages, okay? So, for example, original vector is in 5,000 dimensions. You repackage it into 2 dimensions. The original is collection of words. You package into collection of vectors. Okay? So the criteria you have is sort of like a priori. There's no, this is correct, this is not correct. Okay? So this is unsupervised learning, right? Okay? So that's what word2vec does. It performs unsupervised learning task. But today, when we go inside, when you open up word2vec and see how it operates, you would see that it uses supervised learning tools in there. So don't get confused, okay? Okay. If you promise me not to get confused, we can start looking inside word2vec. Okay? So the whole loop, again, the way I designed this class is a bit like this, right? The big data, focus on analytics mostly on machine learning. Then machine learning, you start with multi-layer perceptron or decision tree working on numerical input as if you were doing statistical analysis. But then I go back and say, well, we're not going to be dealing with numerical inputs for long. We're going to be dealing with picture input. We're going to be dealing with graph input. We're going to be dealing with words input. And these guys somehow have to eventually become numbers. Otherwise, you can't put it in a machine learning, right? At some point, they have to be turned to numbers. Okay. Well, the whole package deal for picture is like convolutional, right? The graph thing, we haven't done much except centrality analysis because it's a very big subject, but it's something that's going to be relevant. And today we're doing word. But word, once again, let me emphasize, you are just doing this bit. Once you end up with this bit, the learning thing is not packaged. Okay? So once you turn words into vectors, you can do all kinds of analysis. And that's what Project Erno-Shield, right? The team Erno-Shield is doing. Okay? Is using words that have been turned into vectors as an input to some model. Okay? So your thing starts here. new thing start here. Okay. But we need to know how word to vec works. And that would clear a lot of misunderstanding. Okay. For that, I sent in the line group the original word to vec papers. Okay. It's not that it's really it's not a difficult mathematical paper. So I would actually encourage you to read it. Okay. But as with academic papers, sometimes it's short on visualization. Okay. So there are a lot of bloggers who write some like machine learning blogs, and they do a very good job of visualizing the problem, visualizing the techniques. And this is one of them. Now, this one I like a lot because of the graphic it has, but it's kind of presenting the story kind of backward from the algorithm, the way algorithm works. So I'm not going to be following the narrative of the blogs, okay? But I would be using the graphics. Okay? I'll be using the graphics. Okay? So this is basically the job. Okay, that's the job, right? It's turning king, man, and woman into vectors. Now, vectors here is numeric, is visually represented as a 4-dimensional vector, right? Vector with dimension 4, right? And the red and blue, that's just supposed to be a value, something like that, okay? So maybe red is high value, blue is low value, it doesn't matter. It's numerical. It's no longer, it's not a color. It's not a color, okay? But think of it as a heat map thing where you turn numbers into colors, okay? Right. What do you want? What do you want? Now, I've mentioned it before, the sort of word algebra. I want to turn the word king into, in this case, 4 numbers. Okay, in reality, it's actually 300, but yeah. Turn the word kings into 4 numbers. Turn the word man into 4 numbers. Turn the word woman into 4 numbers. Such a way that I can do something like this. I like the concept called queen. The concept of queen is like king, but woman. So if you take king minus the man part, add the woman part, should be the queen. That's the concept. That's the semantics of the word, right? When you teach children, well, what's a queen? A queen's like a king, but instead of boy, it is girl. So you subtract the maleness and add the femaleness. Okay? You can think of it as some kind of word algebra. You're doing it in your head. You're doing it in your head. But what you want to do is the vectors to do that. So imagine that you have done the word to vec. What should happen is that the 4 numbers that represents a king minus 4 number that represents man, add 4 number that represents a woman, you get 4 number. You get four more number. And then when you look through some kind of dictionary of which word matches closest to that 4 number, the one that is the best match would have the word queen written on. Okay? It doesn't output the word queen because after all, the computer has to output numbers. It can't output concept. But it outputs a number that you go through the lookup table, right? You can do lookup table, right? And say, oh, what's the closest match? The closest match should be something like queen. And the second closest match may be something like princess. I don't know. Okay? But it should be very far from words like refrigerator. Okay? Has nothing to do with this. It has nothing to do with human, right? So it's very far. So that's what word to vec does. It's very clever, intelligent way Now, again, what is the objective of all this? The objective of all this is so that this can be used as input to machine learning. So it's a machine learning that prepares the data for machine learning. That's why I make the analogy that it's a little bit like convolutional layers, right? It's turning big data, variety data, into vector of numbers, and then you can feed to the multi-layer perceptron type thing. Okay? You don't call that part of convolutional neural network multi-layer perceptron, but I like to call it that. Okay? So it's performing that job. Okay? But the job that it's doing now is completely unsupervised in the sense that, you know, you just tell it in principle. The principle is, well, kings and man and woman are similar concept in some way, right? But king is similar to man, yes, and woman is similar to queen, yes, and so forth. In such a way that you can do this kind of word algebra, this arithmetic, not even algebra, just arithmetic, okay? And you can think of this concept in any way. If you football player, right? You can say something like someone, right, who's very good at passing, say, okay, minus defending at shooting. You can say maybe it's, you know, you see what I mean? It's a concept. It's adding concept, right? Think of concept adding, concept subtraction, concept addition. Okay, if you can do that, that'd be great. So let's look ahead of things like graph embedding. Oh, that'd be interesting. Well, what's the characteristic of graph? That it's very sensitive to key players like Robert De Niro in the network. Okay, it's closely knit. So you want maybe a graph that's closely knit minus the concept of dominance of one guy. Maybe you get a closely knit but more egalitarian, right? Maybe in a not Hollywood, but maybe actors in Thailand are more equal. You know, they sort of like share the workload. There's no dominance like Robert De Niro or something like that, but it's closely knitted. So you adding, subtracting concept. That's what embedding achieves. So that's what we want to do. That's what we want to do. That's basically it. Now, in reality, you have to know two things. First of all, the convention, what seems to work is not 4, but 300. Okay? And this is English words. Okay? Number 2, to do this, it requires some kind of training as well as algorithm. So you have to have some kind of ground truth. So that's why inside we will see uses supervised learning. Okay? Inside this is supervised learning. Okay? You will use it. Okay? But then you will not use the result directly. You use the embedding. Okay. So let's go to. And this is a nice concept of a vector, right? Turning person into a vector, right? Now, the most important, well, not the most important. What's important about vector is you can measure. What's a vector, guys? Vector, if you learn physics in high school, it's like an arrow. Okay? It has length and it has direction. So this is one vector. This is another vector. It points in the same direction, right? But it's bigger. This one points in the same direction, but negative. This one, same length, but points in a different direction, right? So that's why you have this x1 and x2, right? 2 dimension. Okay, what's the length? What's the length of that vector? It's x1 square plus x2 square root, right? Okay. Now, we will not be writing this. We will instead do this. If x is a vector, okay, it's a vector. So this is not a number. This is not a scalar. It's 2 numbers, okay? then this is written as norm of x, so like a double bracket, right? Okay. Okay. Now, obviously, if I have two vectors, this one and this one, two vectors, I'm going to draw different colors. Okay. And then I have another one that's like this, and okay. Black and red. Are they similar? Well, there's two senses of the word similar. This sense is similar because it points in the same direction. Okay? So if you write it as a component 1 and component 2, the ratio is kind of the same, right? So it's similar in direction, but the size is different. Correct? Now, what about this? The size is similar, but direction is different, right? So it depends on your perspective, okay? Is Ayutthaya closer to Chiang Mai, or is Ayutthaya closer to Suphanburi? In terms of distance, Ayutthaya and Suphanburi, same distance, but different direction, okay? Whereas Ayutthaya and Chiang Mai could be in same direction, north, but totally different size, right? Well, the concept of similarity then is called cosine similarity. Okay? Cosine similarity. That's like saying take this and the angle in between is called cosine. Now let me just go to the page just to be proper. Do this. Cosine similarity. And let's get a nice graphic on it. Okay. Okay. Oops. Okay. So you see the double bracket we use? Yeah. The top term A dot B is to multiply the dot product. That's the vector, right? That's the saying. In this case, A and B. So I'll use A1, A2, A3 times B1, B2, B3, right? Multiply them together. Now, think about it. Think about it. If I have something like 1, 3, 2 and 1, 3, 2, which is identical, right? When you multiply that, it's going to get a, what number are you going to get? 1 plus 9 plus 4, right? Now, what if I did this? 1, 3, 2 and 3, 1, 2. 3 times 1 is 3 plus 3, 6, 7, 8. No matter what, if I arrange this in a different order, in other words, if the profile or the ratios are different, the product will be smaller, okay? So the closer they are in terms of direction, the bigger number you get. So that explains the top term, right? But you have to normalize it by the size of the vector itself. So you have to take this times this plus this times this plus this times this. That's the top term. And then you divide by the size of the vector. So that's a cosine similarity. Okay? Cosine similarity is something very simple to do. It's like a dot product, but you normalize it on the bottom. Okay? It's one of the, yeah, I think I should put that on exam because it's very easy to calculate by hand. It's one of the rare things that you can literally calculate by hands on a small scale. Okay? So, what does this do? Let's say I magically turns all of you into vector. Okay? And you are X, you are Y. and you just two-dimensional character, okay? x1 times y1 plus x2 times y2. Divide by square root of x1 square plus x2 square times square root of y1 square plus y2 square. You get some number. That's how similar they are. And you are q. And I say q1 times x1 plus q2 times x2 plus q3 times x3 divided by square root of q1 square, q2 square, right? Multiplied by square root of x1 square. So this number is going to be positive as well, but it's going to be less than that, okay? So you are very far, okay? Now, this automatically works if we're talking about geometric distance, right? If I make you coordinate right now, I start at 0 here. You sort of like 1, 1. You sort of like -1/2 and +3, say something like that. Okay, and you over there would be something like 1.2 and 1.3. So it's very intuitive. It's very obvious that you two are close together in terms of location. The point is we are generalizing this so that the closeness is not location, but the closeness is some concept that you give, which today that concept is called context. Words that appears in similar context will be close to each other in this vector sense, in this cosine similarity sense. Okay, so you don't need to see that anymore. That's cosine similarity, but that's what you want. You want to turn words, you want to turn human beings, you want to turn graphs, you want to turn football player, you want to turn music, you want to turn song, you want to turn movies into vectors, such that is they're close together in some concept. Okay, like movie can be close together in terms of genre or popularity or demographics of audience. You have to define that. That's the concept you have to give to the algorithm. Okay. Now, so the things that you are going to embed, you have to give it the concept of what do you mean by close. In words, it's universal. Well, I think it's universal anyway, that when you're talking about language modeling, the closeness in terms of words would be context. Okay, context. Again, I pet a dog. I pet a cat. So dogs and cats are similar in context, right? Something that I can pet. But I don't pet refrigerator. So refrigerator and cats are far apart, further apart than dogs, right? I also don't pet lions. So lions are not so close. But certainly, I can feed cats and dogs and lions. I don't feed refrigerator. Okay, so in some way you can imagine this kind of hierarchy. Like dogs are close to cats. In turn, they're pretty close to tigers. Okay, but they're a little bit further out. But definitely they're farther away from refrigerator. Okay, something like that. Okay, so you can imagine in your head something like cat minus cute plus eats you equals to tigers. Okay, something like that. Fish minus cute, so you don't get goldfish, at eats you, you get sharks or something like that. Okay, something like that. Okay. So that's what we want to do. Now, this here, this part of the thing just show you the similarity concept at work. I want to use this graphic here. This is the one I like. Okay, this is why I want to use this concept. Imagine that each colors represents some kind of values. Let's go. I'll send you the link. Okay, you can search for it. It's very easy. There are 100 pages on Word2Vec because it's such a powerful tool. Okay, so you imagine that blues and red, the colors represents number, and you want to add king to woman and subtract man, and you get something. Now that something will not map 100% to any words. But if you look up, okay, what you do is you go to your database, you do the cosine similarity of the result with the words, and then you rank them in terms of cosine similarity. You will get something like this. See? You will get something that is close to the top line. I hope this one has the results on it. Okay. So you can imagine, you can do kind of like imagination in your head. You take the king vector minus man vector, right? See, king. So maybe you. Now this is a little bit naive, right? But something like this. You take the king, you minus the man, you add the girl, and you get something that is close to queen, something like that, right? And this is actually the results. This is how you run the thing. Okay, I think this is in this is in Python. Okay, the library, the model library say most similar to positive equal. So this means you're adding concept. What are you adding together? You're adding king and woman. What are you subtracting? The negative concept. So instead of saying A plus B minus C, you say A and B are positive concept and C a negative concept. So what are the positive concepts you want to keep? King, woman. What's the negative concept you want to get rid of? Man. So you get some result. And then this result, you go through the database, compute the cosine similarity for each one, ranks them by the closest. You will see that the word queen has cosine similarity of 0.85. Not 100%, but the closest match. Okay? The second closest match is throne, third is prince, and so forth. Widow all the way down to, and then this is how the algorithm works. Okay, and this is it. This is it. If you have done this, your job is done from a word to vec perspective. Now, if I want to do some kind of modeling, okay, modeling using words. So something like this game, this movie has kings and, predict what's the next word. It should predict queen or something like that. Or not predict. This movie is a story about kings and refrigerator. That's not going to work, right? But this is a movie about kings and queens in the ancient village, ancient medieval time or something like that. That would work, okay? But all that is based on numerical computation. You turn concept into numbers. Now, consider the alternative. What's the alternative? Well, you turn kings K into ASCII number, I into an ASCII number. That's a little bit hard because there's no closeness, you see. So you're not helping the machine learn. Okay? Human beings are very good at doing concept. Okay? Because we don't have to input as number first. We can say input king, input woman minus man. But we can't do it. We don't have to do it numerically, but machine have to. So this is what you have to do. And this is what I mean by this. This block is very good, but it sort of like presents the story backward from the algorithm point of view. So anyway, the key idea is this. What is the word to vec? What is the result of the word to vec? It turns words into vector of 300 long. 300 long, right? Now, first step, what is the first step? You have to encode the words. So you do what's called one-hot encoding. Okay, one-hot encoding. It means this. If you have 1,000,000 words in your dictionary, and you do have 1,000,000 words in your dictionary, right? You do something like this. A, ant, just go through the whole dictionary, okay? What's the next word next to ant? Say ant's the first word in the dictionary. You just make it 1, 0, 0. Okay? What's the next word next to ant? Maybe, well, what's next to ant? N-O-P-Q-R, art. Say the two words, okay? First word is ant, second word is art. 0, 1, and then 0, 0. Okay? What's the last word in dictionary? Zap. Okay? Or Zippo or something like that. And that's 0, 0 all the way 1. Okay? Now, imagine in your head, you have a vector. You want to turn words into vector of size 300 with properties. Now, what I did was just to turn words into vector of size 1 million with no property whatsoever. Okay? There's nothing relating ants and ants. Okay? Just that it's related by order of dictionary. Okay? In fact, it doesn't have to be by the order of dictionary. It just happens to be the most convenient. That's how people do it, right? So you open a Webster dictionary, Merriam dictionary, and you list the first word as 1, 0, 0, second word as 0, 1. Okay? You do this all the way. So what is a word to vec? It's close now, right? You have numbers, right? You just want to turn into numbers. So how do you turn numbers of size 1 million into numbers of size 300? You do matrix multiplication. So a word to vec at the end of the day is a matrix. It's a matrix of size 300 by 1 million. So you take 1, multiply by this, and then you get this. So any word in the dictionary, in English dictionary, let's say the word P, something that starts with P, pan. Okay, the word pan would be 0, 0, 0, 1, and 0, 0 all the way down here because it's one-hearted. You multiply this by this, you get 300 numbers, right? And you can do vector, okay, multiplication. So that becomes the word pan in vector dictionary. So in the future, you can imagine that you open up a Webster dictionary, instead of seeing just the word ant, you see a vector of 300 numbers. Okay? Except they won't do that. Now, so at the end of the day, what you want is a matrix, right? Okay, remember that. Remember that. All you want is that matrix. All you want is that matrix. Okay? The reason I say this is because the creator of Word2Vec is so clever. It's something like this. Have you guys ever done some kind of cooking where you go through the process of cooking the whole dish, but then you throw away the dish? You sort of like want something in between. I don't know, some kind of confectionery analogy to it. It's like you're baking a cake. You're baking a cake, you stick something inside the cake, you bake it, but then you don't eat the cake. You throw the cake away and you eat the inside. Okay? That's what the creator of Word2Vec did. The cake is supervised learning. The inside that you get at the end of the day is just a matrix. That's all he wants. Okay? But he's going to do a whole bunch of things that is tricky and difficult and takes computer time. But once he does all that, he's going to throw everything away and keep just the matrix. In fact, he's just going to use the matrix to multiply by the one-hearted vocabulary and just keep the list of vectors. That's all he wants. And that's what Google did. Okay? I sent the link to the Google implementation of Word2Vec in the Line group yesterday. Okay? Again, your life is so much simpler because Google has done it for you in English, not in Thai. So since your project is based on English words, your life is simple. Okay? The team no shield. Okay. Now, let's see how does that. Well, let's pretend we want to do something. Again, let's pretend we want to eat a cake. So we're going to bake the cake. We're going to bake the cake and then throw everything away and just keep the inside. Okay? Well, let's pretend this. Let's pretend that I want to make a word prediction. If I have a sentence, okay? I like to play with my cat. Okay? I like to play with my cat. Let's say I like to play with my cat, okay? I like to play with my cat. That's 7 words, right? 7 words. So imagine, I like to play with my cat. There are 2 games here. One game is, what if I omit the middle word? I like to play. The word is play. I like to blank with my cat. Okay? Can you predict the missing word? Can you predict the missing word? If you can, good. Okay? So I'm going to make a neural network. Okay? That starts off with 1 million vector, 1 million dimensional vector. Okay? Such that if I put the vector corresponding to I, okay, it also predicts play. Like, play. To, play. With, play. My, play. Cat, play. Right? So in other words, I put the context words and I predict the middle word. Okay? I put the context word and I predict the middle word. That's called continuous backup word, CBOW, backup word. So it's a backup word, it's in front and behind. Okay, I don't know why the name is like that. I don't find it intuitive, but that's the name they go with. Okay, it's called continuous backup word approach. So these are context words. I like to with my cat, and you have to predict the word play. Okay, the other way around is called skipgram. I give the word play, and you have to predict the 6 words. Play has to predict I, play has to predict like, play has to predict to, play has to predict with, play has to predict with, my, and play has to predict cat. That's called skipgram approach. So that's why I wrote in the explanation in the line group last night that there are 2 versions of how to create word to vec. They have different advantages. Okay. The consensus is if you're dealing with rare words and you want to capture the small data, maybe like a secret society lingos or something like that, skipgram is better. But if you want something that's voluminous, driven by volume, large volumes of text, continuous backup word is better. That's just numerically the way it pans out. Now, are you going to make good prediction? Are you going to make good prediction? How do you do this, by the way? You just read through something like a literature. So you go to a library, right? You go to a library and you digitize all the words in the library, okay? So it has 500, 1,000 books. Each book contains 500 pages. Each page contains, I don't know, 20, 30 sentences, okay? And you do this thing. You treat this as training sample. So the way the training sample works is like this. Let's go to the graphic. Again, I like the graphic here. Yeah. So you take something like this. So one case is to base everything you do on Wikipedia. Okay. So you go to Wikipedia, you download all the text. So let's say you get this text. Okay. And the text starts like this. Now, in this visualizations, it's even simpler. It's not 7 sentence. It's not 7-word sentence. It's 3-word sentence. So continuous backup word would be predicting I like cat by I and cat predict like, right? I predict like, cat predicts like. Skipgram would be cat predicts I, cat predicts like predicts I, likes predict cat. Okay. So this word, thou shalt not make a machine in the likeness of a human mind. Okay. So what is the CBOW approach would be? To say thou and not as an input, and predict the middle one, which is shall. You can't see very well, but that's what it is. Okay. So this is thou shall not. The input would be thou and shall predicts not. Okay. Alternatively, if you go to skipgram, you would go the other way. Oh, they use a different example. Buy a red bus in. So buy. Okay. Thou shalt not, okay, this is the same example now. Thou shalt not make a, so not is the input, has to predict thou shalt make a. Okay. So you're predicting, you're trying to do the autofill basically, right? You either autofill the word in the middle or you autofill the word surrounding. Now, is this going to be a good prediction model? Not really. Not really, because people are not Wikipedias. You're not trying you're trying to learn behavior of people predicting from Wikipedia. Maybe that's not a good prediction. It's like saying, are you going to get a good cake out of this? No, you're not. Okay? They train this with the purpose of the intermediate step, because the neural network that does this, will contain 1,000,000 by 300 matrix, right? So the training is supervised learning because you have ground truth, but the model is not going to be very good. But they don't care. This guy doesn't care. He trains it all the way, right? Trains as much as you can. But at the end of the day, just take out the first matrix that multiplies 1,000,000 into 300. It would be something like this by way of analogy. You train a convolutional neural network from the beginning to end, and then you throw away the multi-layer perceptron part and just keep the convolutional layers. It's a little bit like that, okay? It's by analogy. It's not a perfect analogy, but that's the concept. So you end up with this matrix, and then you multiply this. So now that's the end of your job, okay? So now, at the end of the day, you get something like what we saw before. Where are we? With the color there, okay? Now, in reality, there's a tweak. This is something that you guys don't have to be, you should appreciate, but you don't have, you just have to be aware of. A lot of times the techniques that is making a breakthrough, the reason they make a breakthrough is because it's computationally feasible. Remember the convolutional neural network that I told you? Even though Professor Fukushima was trying to work on this in the 80s, he didn't have Game Boy, or he didn't have graphic cards. Okay? So you need the graphic card to do the matrix multiplication to make this viable. Okay? So when in 2010, 2011, this was tried, similar to Fukushima's architecture, but using NVIDIA card, you get the result. The same here. What I'm trying to say is that what I just described to you would not have been computationally feasible. It would take too long. Okay? So instead of training all the whole corpus, okay, the whole language, the whole text that you base it on, it's called corpus. So Wikipedia is considered a corpus, Wikipedia corpus. Library of Congress is a corpus. Now, if you were to train this naively, you have to check correctness or incorrectness with respect to 1,000,000 words. Well, not 1,000,000 words, because it's not just the vocabulary, right? which is the total number of words in the corpus, which is gazillion, billions. It takes too long. So instead of doing this, it's just saying, well, how about this? How about we just learn on the correct prediction? Okay, I like cat, so I has to predict like. I have to predict, cat has to predict like. But certainly, you would never see words like I. What's the thing you never definitely do with cat? Think of a word. I share cat. No, eat. Some people, you can eat cat. You eat cat. It's okay. Probably not good, but you definitely, you don't, I. Okay, and you predict the error. Okay, so instead of, I would say I. Okay, let me write that word. Sorry. Okay, let's go. I cat like. Okay, instead of saying I and cat have to predict like, I would do this. Now watch this. I and like, yes. Cat and like, yes. Then I introduce what's called negative example. I table, no. I refrigerator, no. This is called negative example. So instead of training through the entire corpus, you just pick up the word that is there, the sentence that's there from the corpus, and the sentence that's not there. Okay? This is a very clever computational trick. It reduces in order of magnitude this training task. That's what makes this feasible. It's called negative examples. Okay? That makes sense, right? Instead of trying to learn the whole Wikipedia thing, you just learn whatever is a positive case and then introduce some negative case. Because I never table cat. I never refrigerator cat. Okay? But I can eat cat if you like, right? It occasionally happens. Okay? Now, to answer to correspond to the I eat cat, this is also a 1, but the connection will not be as strong, right? So I like cat is a lot stronger than I eat cat. So this connection, even though you mark it as 1, as a positive, because there's a word I eat cat in Wikipedia. Okay? Okay? Somebody didn't know, so he said I eat cat. Okay, yeah. So it does appear, but not so often. So the connection is not so strong. That's okay. It's going to be borne out in the training. So you do all this. Okay? Continuous back of word or skip gram, but they use negative sampling, and then you train. And that's how you end up with the word to vec. Okay? Again, this is now public information. Now, obviously, what is the recipe? How do you specify the word to vec recipe? What are the recipe you have to specify? First of all, you have to specify what corpus are you going to base it on. Okay, so the word to vec that's run on Wikipedia may be different, would be different from word to vec that's run on Library of Congress corpus. Okay, I am not quite certain what how many corpus has the Google's word to vec, the one that you can use. I don't know what corpus is based on. Okay, so you have to specify A, the corpus. 2, you have to specify whether or not you're using a skipgram or continuous back word. Then you also have to specify the context length. Okay, is it 3 words before, 3 words after, or 5 before, 5 after, or just 1 before, 1 after, and so forth. Okay, but anyway, it's all done for you. But the most important distinction of word to vec result, well, another thing you have to specify also is the final embedding dimension, which again, let's call it 300. Okay, it's kind of fairly universal now. Okay, so the most distinguishing feature of word2vec will be the corpus you base it on. Okay, because the corpus tells you whether or not two words are close to each other in context. Okay, it's going to drive that cosine similarity. So that's that. You don't need to know any more. Well, I don't. You need to know that in Thai language, you have to go to page like a Thai NLP or something like that, where they try to do that. Okay, so this is something that would be run, you can say, in the background. So you can see that this training, this prediction is a supervised learning, right? But the result of the learning, they don't care. Okay, they're not creating a chatbot because it's not going to be very good. But what is good is that the input is a vector of 1 million, and somewhere they make it 300 neurons. That's how they specify to need 300, right? If they make it 200, it'll be 200. So this vector, this weight, the first layer of weight, that's your word2vec matrix. Okay, and then you don't have to even store the original one hot, right? You just keep the vector representation. Once you got the matrix, you run through the entire dictionary and just keep 300 number for each word, and that's it. You're done. You're done. That's why they make it. It's, by the way, have you tried downloading the Google word2vec library? It's going to run very fast because there's no learning involved now. It's frozen. It's frozen. It's saying these are the English words. This is their 300 numbers representation. Okay, so it's going to run super quick. It's a lookup. Okay, there's no more training. The training is done. I don't know how long Google team took to produce this thing. Okay, maybe days or hours. I don't know. Okay, but the point is they've done it, and they don't need to do it anymore unless the corpus changes. So when you download this Google library of word2vec or word embedding representation, okay, word2vec is like a special name for this, but you can say word embedding again. The library will be quite quick. So you look up the word king, there is a vector to it. Not to be online. Maybe there's an online. We can do this. It's an online word2vec mapping that you can put in some words. There should be. There should be map word to embedding vector. Okay, this is all in here. App. Let's put the word app. Embedding projector, maybe. Try that. Now, obviously, this is only going to work in English, I think. So, fetching tensor values. See? So it's fetching the values. Once it fetches the value, yeah, you can. But I think there's something there. But okay. So that's that. I think I don't need to spend any more time on this, right? What I like to do now is then, this is the last working session. This is kind of visualization. I think this is actually embedding the 300 to three-dimensional so you can visualize it, but that's something you don't need. Let's see, what's the word here? So this is compressing the 3 into 3 dimension. Dioxide is close to calcium. Complicated is close to placed. Speed is close to keyboard, snow, ski, iron, ISBN. I don't know if it's not that close, but certainly they're supposed to be like that. Code, programmer, Microsoft. Yeah, those are close words. Basel, Singapore, Oregon, Brandenburg. So these are all cities, I presume. Okay, so these are similar in context because these are places of cities. Composer, Bruce, guitarist. So that's kind of music cluster, maybe. Voter, acknowledged, labor. Oops, this is more like politics. Technologies, mechanics, genetic, memory, protocol. This is like emerging tech. Can you see the words are popping up, right? Yeah. So basically, this is even cuter. So it reduces the dimension of 300 or whatever it is down to 3, so you can visualize. But you wouldn't be using the three number as an input. You use 300. Probably more nuanced, more detailed. Because when you do the dimensional reduction, you kind of reduce the information contained. Yeah. But certainly, this is very interesting. Yeah. Both method tools. That's nice. Investor feudalism. Validity, property, account. This is all accounting term. Huh? ส่งไปใน line. Okay, good. There. Okay. The TA just send this. So this is kind of like an online embedding demonstration. Okay. So this would be on a, so type in the word cat. Now it's not showing you the embedding, but it's showing the nearest, I guess. Cat stuff. Okay, look at university. What's close to university? Student, teacher. It's not giving the score though. I would like to see the cosine similarity. Okay. So this is a demonstration, but it's not as detailed. So it's only saying what are the words closest to university. Now, does it allow you to do algebra here? Positive, negative? ของ collab ใช่ไหม? Okay, send it to the line group. Excellent. Yeah, that's what you guys should do. Yes, loading, application tutorial. Okay, so you can, yeah, good. Yeah, vector similarity. Excellent. See. Yeah, king equal to vocab king, right? And then subtract. Good. Yeah, and it points to that thing as well. Yeah, this is the word arithmetic that we were talking about, except this is shown in 2 dimensions. In reality, it's done in 300 dimensions. It's saying king minus man plus woman, right, becomes queen, right? Good. So what's minus man plus woman? So that's this vector. Woman minus man is this vector, okay? This arrow here, okay? So if king, right, it goes to here. Queen is, yeah. So you can do some kind of vector. You know how to do vector algebra, right? When you add vector, it's like lining tail to head to tail, and you subtract the other way around. So this is a vector man minus woman is tail here, head here, right? Tail here, head here, right? Now you want to subtract man, add woman, so it's tail here, head here. So you take this vector that goes here and you put it to the king. Okay? So this is vector arithmetic. Okay. Now this is a little bit dramatic. You almost get exact result. Okay. But what happened is the exact result will be somewhere close to queen. The point is that you look up all the words here, the queen is the closest. The second closest would be something like princess or something like that. Refrigerator would be way out here. Okay? So that's basically word to vec. Okay, good. Done. We're done for lecture today. Okay, you guys take 5 minutes break, come back. We're gonna have working session on your project.